In lectures 34, 35, 36, we'll be discussing the topic of pointer variables and references. But before going into that topic, let's first discuss a small topic known as type definitions, because the C++ language provides a way to rename existing types. The keyword used to do that is type def, which declares a new name, or which we call a synonym or an alias for a specific type. The syntax is type definition, type def, type alias, where type is the given type and alias is the new name. For example, if you want to, I mean, it's not necessary to do that, but if you want to, you can rename these long type. Even though this is similar to integer, you can rename this long as this name, or you can rename double type as real, and then you can declare variables such as you can just write integer, I mean this name, which behind the scene means long, n equals to 22, or you can just write constant real means behind the scene it means double, and pi equals to whatever number you want to store in this constant variable. And you can also declare the array, such as if you just write integer here, behind the scene it means long, and frequency 64. That means that the array name is frequency, which behind the scene is a constant pointer, and it can hold 64 elements of type double, or type long, because the integer name is an alias or synonym for this type, which is long. And last thing to remember in this small topic is that the syntax, we need to keep in mind that the syntax for the type definition of an array type is type def element type, and then we just write the alias. It shows that the number of elements in an array is not part of its type. Last thing to remember in this type definition topic is that I have said before, that the syntax for an array type is type def element type alias, and it shows that the number of elements in an array is not part of its type. The important thing to remember is that type definition statement does not define a new type. Okay, they are just the names or aliases. It only provides a synonym or an alias for an existing type. Now let's discuss that how many memory locations are possible in a computer. Let's say if I have a 1-bit computer, that means it can I mean, hypothetically speaking, so that means that I can access 0 or 1, just 2 locations. So 2 to the power 1 is 2. So what I'm going to do is I'm going to take the powers of 2, and let's say if I have a 2-bit computer, that means the address line has 2 wires, and they can access using something known as a demultiplexer, which you will see in your logic design course, is 4 memory locations. 2 to the power 2 is 4, so I can access 4 different memory locations, and each memory location would be of 8 bits, or 1 byte. Okay, so 2 to the power 2 is 4, so if I have 2 wires, they can access like 0001, 1011, 4 addresses in memory. And let's say press again, so 2 to the power 3 is 8. If I have a 3-bit computer, that means I have 3 address lines going into the demultiplexer, and I can access 2 to the power 3 8, and from 000 to 888, 000 to 111 to in binary, and I can access 8 memory locations if I have a 3-bit computer. For a 4-bit computer, 2 to the power 4 is 16. For a 5-bit computer, I can access 32 memory locations. Obviously I have 32 addresses, and each address will be pointing to a 1 byte of memory, and each byte is of 8 bits. And if I have for example 6 bits of address bus, or 6 lines in address bus, I can access 64 memory locations. If I have 7 bits of address bus, or 7 lines in address bus, I can access 128 memory locations. If I have 8 bits in computer, or 8-bit computer, I can access 256 memory locations, because 8 wires can have from 0000 to all ones or 00 to FF in hexadecimal. So this is important, 256 number which we repeat again and again. And if I have a 9-bit computer, I can access 512 memory locations. If I have a 10-bit computer, I can access 1024 memory locations, which we call 1 kilobyte of memory. It's actually 1024. We just write 1 KB, B with a capital B, and K is a small, so that's 1 kilobyte of memory for 10 bit address bus or 10-bit operating system. And if I have an 11 bit operating system or 11-bit address bus, I can access 2 kilobyte of memory. And if I have a 12-bit operating system, I can access 4 kilobytes of memory. If I have a 13-bit operating system, I can access 818 kilobytes of memory, and it will just keep on. 14-bit is 16 kilobyte of memory, and it will just, and this thing is a 32 kilobytes of memory, and we have a 64 kilobyte of memory. And if we just keep on going, I mean 64 kilobytes, that is actually 65536, and sorry about the counting, but I think it's 2 to the power 16, so, or maybe 2 to the power 15, is it? Okay, zero from counting from 0 to 15 is actually 16. Okay, so going to, this is 128 kilobytes of memory actually, and this thing is which we call 256 kilobytes of memory. And we have a 512 kilobyte of memory. It's actually behind the scene number is 2 to the power, well, you can just take the log of this number. Okay, and this is 1 megabytes of memory, and this is 2 megabytes of memory, and it will just increase to a really faster rate. And now it's like 4 megabytes of memory and 8 megabytes of memory. I mean, if I just keep on increasing number of bits, I have more addressable memory space to work with, or more memory locations to work with. And this is actually 16 megabytes, which we call, well, 16 megabytes. This is 32 megabytes, and this is 64 megabytes actually behind the scene. That is 67108864. This is 128 megabytes, and this is 256 megabytes, because we call that, I mean, that is actually 268 435 456, that is actually 256. And this is 512 megabytes, and this is 1 gigabyte of memory, and this is 2 gigabytes of memory, and this is 4 gigabytes of memory. So I think I have gone all the way to 2 to the power 32. So if I have a 32-bit operating system, I can access 4 gigabytes of memory. And we can visualize memory as a we can visualize memory something like this, even though that is actually built up in the RAM chips. We are talking about the random access memory chips. So but before going into that, we are talking about a 32-bit operating system here. And if I very quickly go to 64 bits, so 64 bits has this much capacity. 64 bits can access like 1 2 3 4 5 6 7 8, no, this is not 64 bits. I think now we, oh sorry, it just went out of range. So 2 to the power 64 is, I can access like 18 billion gigabytes of memory if I have a 64-bit address bus, and I'm using a computer right now which has 4 gigabytes of memory. So 4 gigabytes of memory is 2 to the power 32. I can access like 4 gigabytes is actually behind the scene this number, and we can visualize, or we can just for we can imagine the computer memory as a very large array of bytes. Each byte is of 8 bits. For example, if I have a computer or a small computer which were there about 10 years ago, and they had like 256 megabytes of RAM, they actually contain like 268 435 256, or 2 to the power 28. So they had 256 megabytes of RAM. This is actually this number. And and if you just visualize this thing as an array, these bytes are indexed from 0 to all the way to 268 435 455, because we are counting from 0. Okay, so the index of each byte is this memory address. Okay, so a 256 MB computer has memory address ranging from 0 to 268 435 455, and in hexadecimal we can say that they go from 0x. 0x is usually the standard format to write the hexadecimal numbers, and we can say that in hexadecimal the index of each byte, which is the memory address, it goes from 0x 00 0, and let me write this number again to figure out how much it goes. Okay, so we can go to this, and if I write 268, 435 and 455, and if I see it in hex, so the index goes from, I mean, we can just write in binary numbers, but binary numbers are quite long, so for short form we just write binary numbers in hexadecimal. So that will go from 0x all zeros to 0x to FFFF and FFF. I mean, we are talking about a 256 megabyte number. So in my computer, if I am using a 4 gigabyte but I'm not so sure if that will convert it here. So if I'm using sorry, if I'm using a 4 gigabyte random access memory, so that will, let me try to 4294 967 and 296. So if I convert it into hexadecimal, so that will go from 0x all zeros to 0x 100000000. So that many locations. So I think no, sorry, I think I should subtract -1. So yeah, so that will go from 0x all zeros to FFFF, because the memory index will go start from 0 and it will go all the way to 4294967 So this memory index is our memory address. They are the index of each byte in our random access memory. So what we are going to do is, if we are declaring a variable, so let's say if I declare a variable integer n semicolon, so it has, sorry about it, this variable declaration associates three basic or fundamental attributes or properties to the variable. Number one thing is the name. The name is n, and its type, which is integer, and its memory address. So let's say for example, if we declare integer n, so it declares the, or it associates the name and the type integer and the address of some location in the memory, in our random access memory in the computer, where the value of n is stored. Suppose this address is 0x0064fdf0, or we can just write any address here as long as it's within the memory space. Then we can visualize n like this. So variable itself is represented by the box. Okay, so this is actually this address, the variable, or sorry, the name of this is on the left of the box, and the variable address is given here. I mean, for our visualization, for our understanding. And in most computers, or as we have seen in the previous lectures, that the integer usually occupies 4 bytes in memory. So the variable n will actually occupy 4 bytes of memory. So you have one, I mean, just write integer here, and we have another byte, and we have another byte. Each byte is of 8 bits. So that will actually occupy the 4 byte block in the memory space, but the address will be of the first byte where this n is actually starting. So this will, because we know the type of this variable is integer, so we can say that this thing is actually occupying 4 bytes, but the address of this will be the address of the first byte in the block of memory where this object or where this variable is stored. If the variable is initialized, I mean, we are declaring the variable and then we just initialize integer n equals to 44, and then the actual representation for us would be, look, n has the value of 44. I mean, we know that behind the scene this is actually 4 bytes, okay, and the address would be of 0x0064fdf0, sorry for bad writing, but the address would be of the first byte only. But since we know the type of this variable or object is actually integer, we know that this address is the first byte, and this object spans, or this object actually occupies 4 bytes of memory, because the standard integer occupies 4 bytes. I think the long integer also occupies the 4 bytes of memory. The long integer actually occupies 8 bytes of memory. So the important thing to remember is that the address of this variable is the address of the very first byte at which the object is starting in the memory. Okay, so in C++, we can obtain the address of the variable by using, let me go here. So we can use the address, and sorry about it. Okay, so I'm going to copy paste this thing, and delete that. Return 0. So in C++ we can use the reference operator. Okay, so I mean the reference operator is the single ampersand. Do not mix it up with the double ampersand, which is the AND operator, which is a logical AND operator. So don't mix it up. So what we are going to do is we are going to write a simple program. We are going to write we're going to declare an integer n equals to 44. Okay, and we just see out the value, the n equals to, and we just write n here, and we just write backslash n. Okay, and then in the next line I just write, this is important, that I write single string, simply n equals to, and this is important, that I'm using the reference operator or the address operator, which we call, and we just write and l over here. Okay, so if I run this code, the just write a pointer value. I'm going to explain that what we mean by this. In my computer, the value of n is 44, and the address of n, where this actually n is stored, like n is occupying 4 bytes, and where this n is actually stored, the address of the first byte is 0x22fe3c, because we can have it's a 64-bit system, right? So my computer is a 64-bit system, so I should be having the addresses going from all zeros to 8f, but actually this is such a large memory space, so it's not actually displaying the leading zeros, which are not significant. So it's actually 22fe3c, but it's not displaying that. So but the important thing to remember is that n is actually stored at this location, and this location obviously 3c, and the next byte would be 3d, and the next byte would be 3e, and the next byte would be 3f. So that will be, since the address of n is the very first byte, how do we know that it spans 4 bytes? Because the type of this n object is integer, and we know that the size of integer is of 4 bytes. So the address here is stored, or where this n is stored, is the very first byte at which the variable n or object n is starting. Now that we have displayed the address of this object using the address operator, we have also used this reference operator before when we discussed functions. In the previous lecture, we discussed this array input output functions.cpp, and we used the reference parameters in the function declaration, so that the function into which the value is passed actually has the address, and it can write directly to that memory location. And the reference, we have further, we will discuss references further in using these references, that the reference is actually an alias, or we can just write alias or a synonym. Alias means a false identity or a nickname, you can call it, or a synonym for another variable. We can declare by syntax something like type, and we just write the ampersand sign, and then we just write the reference name and equals to variable name. The examples are given below, but where the type is the variables type, obviously, and the reference name is the name of the reference, and the variable name is the name of the variable. For example, if I write, the examples are given actually below in this line. If I write integer ampersand rn equals to n, so we can, that means that this rn is a synonym for n. It's just another name for n, and rn is declared to be a reference to the variable n, which must obviously already exist, or already must be declared before doing this line. Okay, so just let's discuss this example. We have declared a variable integer n equals to 44, and then we have declared a synonym rn for n, and then we are see out the value of n and the value of rn, and then we are decrementing the value of n, then we are we are printing the value of n, and then we are also printing the value for rn. And then just keep in mind that rn is actually a reference, or they are essentially two identifiers. We are talking about n here and we are talking about rn here. They are essentially two different names or two different identifiers for the same variable, which is actually n. So they always have the same value. Okay, so decrementing here, n changes the value of n, and rn basically a synonym or alias for n, to 30 to 44. That would be 43. We're going to run that, and then we are multiplying the value of rn. Essentially this is an alias for n, so we are doubling the value of this variable n, or with an, or also a nickname with a with a synonym rn. Okay, so this thing, let's first run this thing and see what we get. The value of n is 44. The value of rn is obviously 44 because rn is a synonym. Value of n, we decremented that, is 43. The value of rn is a synonym for n actually is 43. And then we doubled that. The value for both of these things is actually 86. So essentially they are two names for the same object. Okay, so the like constants, you have to initialize them at the time of the declaration. The references must be initialized when they are declared, but unlike a constant, a reference must be initialized to a variable, not a literal. This is extremely important, that the reference must be initialized to a variable. I cannot write, for example, I cannot write integer ampersand, and I can just write rn equals to 44. This is huge error, because the reason is that 44 is not a variable, and you might see a warning in some compilers. Some compilers will just refuse to compile this code, but some compilers might be creating a temporary variable and creating a warning to do that, but this is actually an error. Okay, this has to be some kind of a variable which must have been already declared. 44 is not a variable. We can write a variable name here, that should have been declared before that. Okay, so using so we can say that a reference must be initialized to a variable, but the reference is not a variable. That is extremely important. A variable is an object. It is a blocks of contiguous or continuous bytes of memory used to store information which is accessible by the program, and different objects obviously occupy different point blocks in memory, obviously. So we have let's say another example that these references are not actually separate variables. They are essentially the names of the same variable. So we have declared a variable integer n equals to 44. Then we have declared a reference, and we can say integer ampersand rn equals to n, and rn is just a synonym for n. And then we are printing the value of the address of n, and we are printing the value of address of rn. Okay, and then we are declaring another reference to n, and this rn2 is another synonym for n. Okay, and this rn3 is another synonym for n. Now we are printing the values of the address of rn2, and we are printing the values of address of rn3. So if I run this code, it says that the address of n 22 FE34, address of rn 22 FE34, address of rn2 22 FE34, and address of rn3 is 22 FE34. Essentially they have the same address, or we can visualize this, that this 22, I think it's 22 FE34, I've written that earlier, that we can visualize this thing as that we are talking about the same object. The name of that object is n, or it is also known as rn, or it is also known as rn2, or is it also known as rn3. And these are just the synonyms or alias for this variable or object n, and it contains a value 44, and it is stored at this location 22 FE34. That is the address of the very first byte. Because this variable n, also known by this name or this name or this name, actually occupies 4 bytes of memory, but the address which we store, or address which is displayed here, is of the first byte. So let's discuss this code a little bit further. Let's minimize that, and let's discuss this code a little bit further. And the first line or this output here, this first line of output show that n and rn have the same address and they are merely different names of the same object. The second shows that an object can have several references and that a reference to a reference is the same as a reference to the object to which it refers. In this program there is only one object, an integer named n, and with the address of 0x20 through fe34, the names rn, rn2, rn3 are all references to the same object. In C++, the reference operator is used for two separate purposes. When applied as a prefix, let me write down somewhere that here, I mean this is just discussion. When applied to a prefix to the name of an object, it I mean some such as if I write, I mean the name of the object is n, for example, if I write m%n, it forms an expression that evaluates or yields the address of the object. When applied to the suffix of type t, I mean for example if I write I mean these are all comments really, when applied to the suffix, suffix means coming later, and if I'm talking about the prefix comes before. Okay, so when applied to the suffix of type t, it names a drive type reference to t. For example, integer m% is a type reference to integer, which we have just done before. So in the previous example, n is declared to have type integer and rn is declared to have type reference to integer here. Okay, so I mean C++ has 5 kind of drive. That is kind of a theoretical topic here. So if t is a type, then constant t is a drive type, constant t. Okay, t with these round brackets is a drive type saying that function returning t, and t with the square brackets is a drive type saying array of t. T ampersand is a drive type reference to t, and t star is a drive type pointer to t. So I mean references so far are used mostly for reference parameters. I mean if we are passing the address directly, and we see that they essentially work the same way as the reference variables in this example from the previous lecture, because they work as the same. I mean they are the synonyms for alias. They are merely synonyms for other variables. Obviously, reference parameter for a function is really just a reference variable whose scope is limited to the function. So the reference operator, this reference operator returns the memory address of the variable to which it is applied, and we saw that how we can use that to print the address. We can also store the address in another variable, such as here. I'm going to explain that in a moment. And this type of variable that stores an address is called a pointer. Like that. Okay. The pointer variables have the drive type pointer to t, and where t is the type of object to which the pointer points, so the types must match. And the drive type is denoted by, which we have seen, is t star. I mean that is, I mean for example, address of an integer variable can be stored in a pointer variable of type integer star. Now in this example, in which we are going to use the pointer variables, here we have declared a integer n equals to 44, and we are we are printing the value of n, and we are printing the value address of n here. Okay, and then we have declared a pointer variable of type integer, okay, pointing to integer pn, and in this variable, this is a special type of variable, pointer variable, we are storing the address of n here. Okay, now we are printing the value of pn, what is stored in pn, and then we are also printing the address of pn. So let's see how it works. So I'm going to run this program, and it says that the value of n is 44, okay, and the address of n is 22 fe3c, and the value of n and the value of pn is storing 22 fe3c. So pn is actually storing the address of n, and here what we, and the variable pn is actually initialized to n, which is the address of n. So the value of pn is actually the same address at which the value stored at pn is the address where the first byte address of where this variable n is stored. and but pn itself is a separate object. It's stored somewhere else, obviously, because that's a variable. Pn itself is a separate object. So this pn itself is stored at 22fe30. So I've drawn the figure in this node, and it says that pn has the address of this object. Okay, and the type here is integer star, obviously, and here in this example, in this figure, it's actually much more clear that the value this object stores 44 in this 4 bytes. The address of the first byte is 22fe3c. This number 22fe3c is actually stored in this pointer variable 22fe3c here. So that's the value of this pointer variable, but this pointer variable is itself stored somewhere else in the memory, and the address here by this line is saying that 22fe30 is the address of this pointer variable. So this variable pn is called a pointer. Okay, and because its value points to the location of another value. The value of a pointer is an address. Okay, and that address depends upon the state of the individual computer on which the program is running. I mean, you can have different address if you run this code. That is not relevant, but the important thing is that this variable can store the address of another variable. Okay, so this this diagram, I mean, if you run this code in your own computer, this diagram is not going to match, because you might be running separate kind of a different memory space, so depends on what is actually running. So obviously, I mean, there is a huge chance that you're going to get different values here, but the important thing is this variable can store the address of another variable. So usually we have different values every time we run the program, or every time we run the program on a different machine. So we draw the address, so we draw this figure like this, that this pn is pointing to this n here. So this captures the essential part, that pn is a pointer to n, and n has the value of 44. So we can think of this pointer variable as a kind of a locator. I mean, it locates another object, so it stores the address of another object, so it locates another object. So how can we use this address to access this? Obviously, we can use n equals to 44, we can override the value of n equals to 55 or something like that, but we can use this variable to access this, because obviously we are going to use the pointers which store the address of this variable. So what we are going to do is we are going to use the dereference operator. The dereference operator is given here, the star operator, and the logic here is that if pn points to n, we can obtain the value of n directly from pn, and from the expression pn, that pn, and this star operator, this star pn evaluates to the value of n. This evaluation is called dereferencing. We call dereferencing the pointer pn, and the symbol star is called the dereference operator. So in this program, I've declared, the same example actually from here, and here integer n equals to 44. Okay, see out the value of n equals to this, and the ampersand n means we are talking about the address of n at which the n is stored, or the address of the first byte, and integer star pn equals to address of n. That means we have declared a pointer variable pn, and that is going to store the address of n here. So we are going to print the value of pn that will contain the address of n, and pn itself is stored somewhere else, obviously, so we are also going to print this value of the address where pn is stored. And in the last line, this is different, we are printing star pn. Okay, so we are using the dereference operator, and essentially we can say that star pn is an alias for n, and they both have the value of 44. So we can use, if you are using this star pn, that means we are saying, look, use this address and go to whatever location it is pointing at and print whatever value is stored over there. So if I'm using star pn, so I'm essentially saying that if I write star pn, I'm actually using this address to go to this location, and whatever is stored at this location, I'm going to print that in this cout statement. So let's see that what we get. here. N equals to 44. The address of n is 22fe3c, and pn stores this value of this variable n, and star ampersand pn is the location at which this itself pn is stored, and star pn is just an alias for n, and we are using the dereferencing operator star pn to access the value of n, saying that look, pn contains the value of this address. Okay, go to this address and see what is printed over there. So this 44 is printed at this point. Continuing from this example, now we can have something known as pointer to pointers. Obviously pointers is stored somewhere, they contain the address of some other location, and pointers themselves are very special variables, and they are stored at some location. So we can address this, we can store the address of those pointers in another pointer. But let's see, I mean, building from the previous example, we can go on and on for that. Let's say we have declared a variable integer n equals to 44, and the value of n, the address of n is going to be printed, and this pointer pn will contain the address of n. Okay, so pn will contain the address of n, and the ampersand pn will display the ampersand pn will display the address where pn itself is stored, and star pn will dereference pn and saying that look, pn has the address of n, star pn will contain the value of n. I mean, using the address stored at pn, I'm going to the location n, and I'm going to print whatever is stored at whatever is stored the at location n. Okay, so now what I'm going to do is I'm going to declare another pointer integer star star ppn, and that will contain the address where pn is stored. So ppn holds the address of pn. Now ppn will contain the value of the location at which pn is stored, and ppn is just obviously another object, it was stored somewhere else, so we are going to print the address there, and star ppn will going to dereference ppn. Okay, and that will display the value of pn, whatever is stored over there, and double star ppn is going to further dereference that, and we will arrive at n. So let's see how it works. So first I'm going to run this code. So value of n is 44, and the address of n is 22fe3c. pn contains a pn is a pointer to n, so it contains the value 22fe3c. pn is stored somewhere else, so it is stored at 22fe30. Star pn, I mean dereferencing using the address here stored, using the address stored at this thing, we arrive at n, and the value is 44 is stored. ppn has the address of ppn. Where is ppn? ppn has the address of pn. Okay, so ppn has the address of pn, so same address here, and ppn itself is stored somewhere else, so it's stored at 22fe28. and if we dereference ppn, so that will yield the value which is stored at pn. The value pn is a pointer, so it has some address, it has some address and is storing some address, so that stored address is stored displayed here. And if we dereference that as well, you know, dereference ppn, we arrive at this location, so which is here. So I mean, if we just dereference double times, I mean twice, we arrive here. Single dereferencing, we arrive here. Double dereferencing, we arrive at this point. So single dereferencing was displaying the value which was stored at pn, which was the address of n, not the value of n, address of n. And double dereferencing, what it does is it arrives at pn, using that it arrives at n, and it displays the value 44. So coming back to code and the output, so the variable ppn just points to pn, which points to n. So the star ppn is essentially an alias for pn, just as star pn is an alias for n. Therefore star ppn is also an alias for n. So in this example, each of these three variables, let me write it down somewhere, each of these three variables, n, pn and ppn, has different type. I mean, they have different type. I mean, they have integer, and we have integer star for pn, and then we had integer star for ppn. So in general, if t1 and t2 are different types, such as, I mean, t is a different type, t1 is a different type, and t2 is a different type, then any of their drive types will also be different, obviously. So although pn and ppn are both pointers, but they are not of the same type. That is important. Pn has a type pointer to t. Okay, pn pointer to pointer to integer, not t, and while ppn has type pointer to integer star. That's why we use double stars. The reference operator, I mean in this scenario, or in actually pretty much every scenario, reference operator and the dereference operator, they are inverse of each other. So we can write n equals to is true, p, whenever p equals ampersand n. Or I mean, I can also these are inverse, so I mean you can just write if you have done Fourier transform. No, you have done that. Let's say if you have write sine inverse and sine of something, and you take sine inverse of that thing, you get the same value at which you started. So I can just write star ampersand n is actually equals to true to n, and I mean if that actually matches. Or we can just write ampersand star p is actually equal to p. So I mean that will yield to true. So we can say that the referencing is obviously the opposite of dereferencing, or the star and the ampersand operators are actually inverses of each other. So building upon this program, let's say if we declare a variable integer n equals to 44, and we print the value of n, and we print the value of the address where the n is stored, and then we declare a pointer pn, which can point to an integer and is store the address of n in this pointer pn. So we will be displaying the value of pn, but obviously that will be the address of where n is stored, or the first byte where n is stored. And in the next line, I'm going to print the address where pn itself is stored. So obviously pn is stored somewhere in the memory, so we are going to print the address where pn itself is stored, and then we are going to dereference pn, and we're saying that wherever pn is pointing, go to that value, and that value is obviously going to be the value of n. And let's run this code. If you run this code, the value of n is 44, and the address where n is stored is 22fe34, and pn holds a value of the same address, 22fe34, and the pn itself is stored at 22fe28. And if we dereference pn, that means that we are saying that pn has the address of n, go to that address, and whatever value is printed, so the value of n is going to be printed. Now in the next line, I've declared another variable nn, and that is going to hold the value 44, because pn is pointing to n, and if we are dereference pn, so that means the value of 44 is going to be stored in nn. And the next line, I'm storing the value of nn and displaying that. So nn contains 44, and the address of nn, obviously that's a separate object, so it's stored at 22fe24. So this is actually different location. And then we have created another alias or a reference for and the name of that alias is rpn, and this is just will contain the value of 44, because rpn is just another alias or reference for n, and we are going to print the value of rpn, and that is 44, and address of rpn is exactly the same as the address of n. So if we look at the picture, which says that nn44, and the address 22fe34, that is stored at pn, and if we dereference pn, star pn, we approach the value of 44, and nn contains a value of 44 because nn was declared to be star pn. So nn variable was declared, and it contains the value star pn. So star pn is actually the dereferencing pn, and we end up with 44. So 44 is also here, but the address where n is stored is different as this n variable. They are stored at different locations, and so is the pn pointer variable. This is stored at another location, and it contains the address this value. And rpn is just an alias or a synonym, so the address of rpn is exactly the same as the address of n here, and the value of rpn is exactly the same as the value of and the address and the value of rpn is exactly the same as the value of n. So rpn is essentially an alias for n here. So the values and so here, so just to summarize, here p points to an integer named np, and rmp is just a reference, that is initialized to the value to which Pn points. So Pn references an Rpn, D references Pn here. Therefore Rpn is an alias for n, that is they are different names for the same object. This output verifies this, and RN and Rpn have the same address, which is 22FE34. Like the reference operator, which has to use this, the dereference operator, which is a star, is used for two separate purposes. When applied to a prefix to a pointer to an object, it forms an expression that evaluates to that object's value. When applied to a suffix, which comes after it, to a type t, it names the derived type pointed to t. For example, if I write integer star, so that means that it is a type pointer to integer. Okay, so which we have discussed the drive types before, that C++ has 5 kind of drive types, and we just to look at the examples of how to declare the drive types. So we have constant integer C, well, that's a constant integer. Integer %rn, so that means we are making a reference rn to n. Integer star pn, so that means we are talking about the pointer to an integer. The name of that pointer is pn, and it is storing the address of n. So n has to be obviously declared earlier, and that's it. And integer a, and this thing, the square brackets, so we are talking about an array of integers, and this we will see later that since I am running out of time, because the time allocated for now 3 lectures is actually, or 3 labs is 50 minutes only, so I'm just going to finish it up with this last topic, and the array topic will continue in lectures 37, 38, 39. Okay, so this a is a constant pointer. We will see later that array name is a pointer, and here since we are discussing drive type, so we are talking about array of integer f with these round brackets, so we are talking function. So we are talking about function which returns an integer. So wherever this function is called, it's going to return the value 33. I mean, this is a single line function here. A drive type can derive from other types as well, so I mean there are lots of combinations which are possible. So if you write integer star constant pn equals to 44, so we are talking about a constant pointer to an integer. You might be using these constant pointer because you have the address, but you really cannot overwrite whatever values are given there. So but you have the address to access that location. Then you can just write constant integer star pn equals to %n. So we are talking about a pointer to a constant integer. Then constant integer star constant pn equals to %n. Then we are talking about constant pointer to a constant integer. Then we have a float %ar, and this is an array of 2 references to floats, and float star ap with the square brackets, so we are talking array of 2 pointers to floats. And then we have long %r round brackets, and this is a function returning reference to long. And then we have long star, and this is a function returning pointer to long. So 2 separate things. These are essentially, I mean, whatever is behind whatever is written before the function name, that is a return type. Then we have long star pf, so we are pointer to function returning long. So this might get a little bit technical, so, but just to emphasize. And then lastly, some drive types require the assistance or the help of type definitions, which we saw in the very beginning. So we can just write type def char word 255, so it's a type array of 255 characters. Then we can just write word %pa equals to a. This is a reference to an array of 255 characters, and word star pa equals to %a. This is a pointer to an array of 255 characters, or shall we say that pointer to a may be a pointer. We will see later that a itself might have been a pointer. Okay, but we will discuss that in the next lecture.